Good morning, good afternoon, and good evening, wherever you are. I'm Ausdang Thangthai. Today I'd like to talk about our digital generation system that we submit to the challenge. This work aims to build a digital generation system from both acoustic speech and textual information. In terms of text input, we propose the use of a combination of phonetic and word transcription. We believe that the extra information from phonetic can generate better gesture movement. So today I will tell you about how we prepare the data, how we extract the input and output feature, and then how we model the gesture. Moving on to the data preparation, as we would like to use the phonetic transcription, but unfortunately, this doesn't provide in the 3D dataset. They provide the speech and word transcription. What we like to do the automatic force alignment to find the timestamp of a phonetic transcription in the speech segment. This is what we're going to use the Montreal force aligners as a toolkit to do that job. And this require audio, text, and dictionary. Yeah. From the original dataset, we get just only the audio and text information. We don't have dictionary, so we have to find the kind of data. What we need to do, we have to convert the text to phoneme. In this case, we use festival live, I mean the live version of festival. And festival is speech synthesis toolkit. For the input text, we can get a sequence of phonemes. So we can, and the second step, we can build the pronunciation dictionary. From there, we can get a pair of word and pronunciation. So after that, we're going to do the force alignment using Montreal force alignment. Then we'll get the output like this. That means we can find the beginning and ending of each phone in the speech segment. The first problem is we found that some part of the word transcription is missing. And this incomplete word transcription leads to misalign. That's the problem. And the next problem is when we process with long audio files, please bear in mind the average length of the 3D data is about 10 minutes. It's too long. Based on our experiment, sound file should be less than 30 seconds. So what we try to do, we try to segment the long file into shorter version. We try to segment into sentence. So we end up, instead of, we use 2,000 sentences instead of 23 recordings for the force alignment. So that's all about data preparation. And the next step will tell you about how we extract the input and output features. Moving on to input feature extraction. For speech features, we extract 26 order of MMCC and F naught and energy with its derivative. With text feature, we have a lot of features vary from frame level to phoneme level to sentence level. Okay, let me show you some example of the text feature. First, let's show you how we extract the current phoneme features. We have to extract the feature frame by frame, right? And for example, in this case, if we would like to extract the feature as frame 7, the current phoneme of frame 7 is M, but we can't use the M symbol. We have to convert M symbol into some numerical. In this case, we convert M symbol to the vector we call one hot vector. That means the index of phone M is set to 1. Another example is about acoustic class features. The output of this feature is 57 binary vectors. Again, if we look at frame 7, this question, this feature is based on question. For example, is the current phoneme is vowel? Is the current phoneme is consonant? Is the current phoneme nasal sound? So phone M is a consonant and phone M is a nasal sound. That's why we set 1 at the second index and the last index for this feature. And the next example is about phoneme context features. Again, at phone 7, we like to find the queen phone context. That means we have to look at the 2 preceding phone and 2 succeeding phone. We get this kind of window. And then we convert each phone with a one hot vector. And we also use word embedding features. Again, at frame 7, at frame 7 is come from the word most, and then we find the word embedding of the word most. We use the pretend model that in this work we use the pretend model from Spacey toolkit. Yeah, moving on to the output features. For the output features, we didn't use the raw motion gesture. We use the bottleneck features of the denoising autoencoder instead. More details can be found on Kucherenko's paper. The last step, we go into model, we get the input and output feature, we go into model. And then in this work, we use an encoder, decoder, bidirectional STM architecture. Here it's about, it's about encoder part, decoder part. We encode everything into context vector, and then we decode the output from the context vector. The output vector is we need to pass the output vector to gesture decoder that come from the denoising autoencoder part, and then finally we can bring the motion back. So look at the result. The first thing we found that natural gesture motion show the highest rating in both N and M condition. It wasn't surprisingly that N condition is the best. But so if we look at the video,
like, oh, okay, well, okay, whatever. And I was just like, why have you done this to me?
Yeah, but personally, it was surprising that M condition is better than generated system in the challenge. I mean, at the first step, I personally think M condition could be bad, but then when I look at the video result, I changed my mind.
Like, oh, okay, well, okay, whatever. And I was just like, why have you done this to me?
Yeah, I think it's still okay. It looks okay. If I didn't tell you that there's a mismatch condition, you might think, oh yeah, it's kind of like a natural condition. With our approach, it's labeled with as A. We got a fair rating result in terms of both humanliness and appropriateness. Yeah, it's all about 50. Okay. Look at some video
I was just like, oh, what if? Who knows? I have a girlfriend. I live with her. I'm very happy, so it's no big deal. But it's interesting how those things work out sometimes.
Yeah, I think overall it looks okay, but I think it still have a lot of things to improve. I personally think if we can improve two important motion like hand and head movements, we sure we will get the better result. For the other videos, I think yeah, I found it's a bit jerky from the video output. Even we apply the smoothing technique, and then first I would not like to apply the smoothing because when we apply the smoothing process, it's going to over smooth to the output video, and yeah, and the another important thing I think in the future, I think we need to find a way to find the relationship between the word we speak and the movement we act if we like to improve the system. Yes, that's all about my presentation. Thank you very much. Bye.